Welcome to the 8th tutorial of the RISC-V Architecture and Assembly Language series. In this session, we're going to look at floating point arithmetic. First of all, we will cover floating point in a more generic sense. This means that the information will be general and is applicable to not only RISC-V, but also ARM and x64-based processors. It will adhere to the IEEE standard 754. There will be a few examples, and then we'll examine the capabilities of RISC-V as it pertains to floating point. If using real RISC-V hardware, which is recommended, ensure that the SBC has floating point capability. This is the case for the SBCs referred to near the beginning of this tutorial series. Floating point differs from the integer arithmetic that we have covered so far. The range of our numbers has been limited in size. Whereas, floating point covers very large and very small numbers that are used in many scientific applications. Rounding occurs with both decimal and floating point numbers. Since exact number representation is not always possible, the general form of a floating point number is the mantissa, or the significand multiplied by the base to the power of the exponent. Here, the number 286.35 in general form is 2.8635. multiplied by 10 to the power of 2. The standard use is binary. So when calculating floating point IEEE values, the first stage is to perform binary conversion. So in our case, the base will always be 2. The standard covers areas such as rounding rules, where a number may be rounded upwards or downwards depending on the least significant digit. This is a familiar operation in base 10, where a number such as 3.356 would be rounded to 3.36 to 2 decimal places. There is also provision for not a number, known as NaN. An example would be the square root of a negative number. Plus or minus infinity are also catered for. There is a term we will deal with called bias, which will allow the number representation to split over near equal quantities of negative and positive values. Single precision and double precision floating point numbers are included in the standard. An example of bias is shown where the bias value is 2 to the power of n-1 where n is the number of exponent bits. With single precision, there are 8 exponent bits, so this bias value is 2 to the power of 8-1, which is 2 to the power of 7-1, which gives a value of 127. We can work out the value of the biased exponent by subtracting 127 from it. In this example, an exponent of 1001111 in decimal is 155 minus 128, which equals 28 decimal or 1110 binary. The way the standard conveys not a number and infinity numbers to us is by using the bias value. If the exponent has an all ones value, then it represents minus infinity. Since the signed bit is negative, if the most significant bit is a 0, then it represents positive infinity. The fractional part is all zeros. Not a number is represented by the bias exponent being equal to all ones along with the fractional part being non-zero. The sign bit for not a number is don't care. The table shown summarizes how not a number and infinity are represented. Quiet not a number and signaling not a number are two representations of not a number. With signaling, an exception can be raised when not a number is encountered. And with quiet not a number, it does not signal an exception. Now we can dig into bias a little deeper. It is basically the ratio of positive values to negative values. The standard sets it to equal representations of each and the values are symmetric. The diagram shows the concept of bias. The use of asymmetric bias would only be used in specific cases which exhibit skewed values such as only positive values. Note that bias values represented in the standard is only discussed here. The IEEE standard does not discuss asymmetric bias schemes since it is designed to suit general-purpose computing. To summarize, the sign bit indicates polarity. The significand is the fractional part. The exponent is stored with a bias. Normalization is a process of shifting the binary point so that there was only one value to its left. So a number such as 1011.01 would become 1.01101. Since the numbers are normalized with this leading 1, it need not be recorded. Instead, it is implicit. This saves another bit. There are some cases where normalization does not apply, such as an all-zero number. Note that the standard uses the term significand rather than mantissa. Mantissa is more closely associated with logarithms. Single precision floating point uses a total of 32 bits. These bits are broken down into an 8-bit exponent, a single bit for the sign, and 23 bits for the significand. As mentioned earlier, the leading 1 to the left of the binary point is not stored and is implicit. Double precision uses 64 bits with a single sign bit, 11 bits for the exponent, and 52 bits for the significand. The precision for decimal representation with single precision is of the order of 6 to 9 decimal digits. And for double precision, it is in the order of 15 to 17 decimal digits. So this gives you an idea of the accuracy that can be expressed. The bias for single precision is 127, and for double precision, it is 1023. To take an example, if a single precision floating point number's exponent had the value 101 binary or 5 in base 10, then the stored exponent would be 101 plus 111111, which equals 10000. 010 or in base 10, 5 plus 127, which equals 132. A summary of the precision that can be represented by single and double precision is shown here. This example shows how to encode a decimal number into a single precision floating point number. The first step is to convert the decimal number to binary. The part to the left of the decimal point is straightforward, as 13 is equal to 1101 in binary. The fractional part can be computed using the algorithm shown on the right. Here, you multiply the fractional part by 2 until the value is 0, noting the value to the left of the decimal point. Here, multiplying 0.25 by 2 gives a value of 0 to the left of the decimal point, and 5 to the right of the point. Multiply again. And this time there was a 0 to the right of the decimal point, so we stop, and we record the value of 1 to the left of the decimal point. Recording the values to the left of the decimal point from the top down gives a value of 01. So the full converted number is 1101.01. Next, the value is normalized by shifting 3 places to get 1.10101. The number then is 1.10101. The bias for single precision is binary 111111 plus the stored exponent of 11, which is 3 in base 10, giving binary 10000010 for the exponent value. We drop the leading 1 to get a significand of 10101 and pad the remainder of the field to get 10101000. All the way out to fill the bit field. Now construct the full value with the sign bit, the exponent, and the significand. To get a full 32-bit number of 1100, 00010101, and the remaining bits are all 0. If you're wondering about the exponent 3 number, real that when we shifted the number, we shifted it 3 places, and this is why we have the exponent of 11 binary. We'll be giving you some more examples soon. Hopefully, it's clear enough from what you see there. This next example is very similar. It just shows how to encode a decimal number into double precision floating point. Again, the first step is to convert to binary. The part to the left of decimal point is straightforward. As we saw before, it's 13. The fractional part can be computed using the algorithm, so it's exactly the same as we had before. The full converted number then is 1101.1. Now we've normalized the value as we did earlier, so we get 1.10101. Again, we'll shift it 3 places. Now the bias for double precision, though, is different. It's 1023 in decimal. We add in the stored binary exponent of 11, and that gives us a total of 10000010 for the exponent. We drop the leading 1. Because it's going to be implicit, and we get a significand of 10101. And, again, we pad the remainder. But this time, we pad it all the way out to the full 52-bit field positions. Next we construct the full value with the sign bit, the exponent, and the significand to get the full 64-bit number, which you see there at the bottom of the screen. I've color-coded this, so the green part is the significand. The blue part is the exponent and the red part is the sign bit. Again, there's no better way of learning this than working it all out by hand. You could use a spreadsheet and then make the cells fairly small. That way, you won't make any silly mistakes when you're adding or anything like that. So that's my recommendation, and that's how I've done most of my calculations by hand in this series. So we've done encoding. Now we need to look at decoding. This example shows how to decode a floating point hexadecimal number into regular base 10 notation. The first step is to convert to binary. After that, we determine the sign, which here is negative. We break down the bits to show the exponent and significant fields. The true exponent is 9 since the field breaks down into 136 decimal, and subtracting 127 from this number gives 9. Add in the implicit bit to the significant field. Converting the fractional part gives 0.10742185. Multiply the complete significant 1.10742185 by 512 to get 567. The reason we used 512 is because that's 2 to the power of 9. So the final value is minus 567. Don't forget the sign bit. So, hopefully, that's clear enough. If we want to add numbers in floating point, that's fairly straightforward. The major task that we have is to line up the exponents. To equalize the exponents, we take the lower number, and we shift over the binary point the required number of positions. So if one exponent has a bias of 136 and the second has a bias of 134, then the second number will need to be shifted across two places to make the exponents equal. The way we do this is we shift the significand to the right two places. Now we should already be familiar with this kind of operation in base 10, where the general case is multiplying the significand by the base to the power of the exponent. So a number such as 9000 by 10 to the power of 3 can be expressed with an exponent of 6 by diminishing the significands. Digits from 6 to 3 places to the right to get 9 by 10 to the power of 6. So 9000 by 10 to the power of 3 is equivalent to 9 by 10 to the power of 6, and that's why we move over to the right. So here's a graphic example of all the different steps. And, again, this was done with the aid of a spreadsheet so that I wouldn't get the numbers misaligned, and, again, highly recommended. Both numbers' exponent fields are converted to decimal, although you can do this directly in binary if you are fluent enough. It shows they differ by a value of 3 or 1 in binary. We equalize the exponents by adding the implicit 1 bit and shifting the second number's significand over by 3 places to the right, and this gives the value shown. The next stage is to add the first number significand to the new significand of the second number. Now since the addition spilled over and generated 2 digits to the left of the binary point, the result must be shifted back 1 place to the right to renormalize. The shift has caused the exponent to be increased by 1. The new exponent field then is 135. Assemble the fields, again, dropping the implicit bit to give the final result of 01000, and you can see the rest of it in the diagram. So this is a little bit tedious. And if you're just used to programming, you can just take it for granted that RISC-V will do all the calculations for you. But if you do want to go behind the scenes or are studying computer science, that's the idea of this first part of the tutorial 8, it may be worth it. Later on, we'll be just executing assembly floating point instructions and looking at the result. But this will give you an idea of why the registers hold the data that they do. The GDB register view shows the raw IEEE values as well as the double and the single precision number. So it does help you to have a background in this. Alright. Heavy going. But we've now reached the second part of the tutorial, so stick with it. Now that we've got a basic grounding, it's time to look at how RISC-V can handle floating point instructions. So first of all, let's look at the floating point registers. They are similar to the integer X registers that we know about. There's 32 floating point registers. They also have ABI alias names, which should be adhered to along with caller/callee responsibilities. We use the term FLEN instead of XLEN for the register width. In this session, we're only going to cover single precision and double precision floating point. As you've seen, we've already discussed their anatomy in the first part of the video. And if you're not watching this all in one go, it might be opportune to review this. We also have half precision and quad precision, which we won't discuss. Mainly, I'm going to be covering 64-bit operation with single and double precision. We will not discuss half and quad precision architecture. The capability of the RISC-V processor will be denoted by RV64 for 64-bit, followed by letters indicating the floating point capability. And, again, you can do in software with the command cat/proc/cpu info if you are running under the Linux operating system. We're going to have an overall view, first of all, of the floating point instructions. They are broadly based into categories such as arithmetic, and then load and store instructions. Some of the arithmetic subcategories that might be of interest are square root and minimum and maximum instructions. So this is something we didn't meet with the integer arithmetic tutorials. So this is new to us as well. There are categories of instructions to convert data between integer and floating point with single and double precision variants. In addition, there is a complement of comparison instructions. Be aware, however, that while integers have exact representation, this is not necessarily the case with floating point. More about that later. The field format of a floating point instruction is fairly similar to what we've seen before. This is a register type instruction. So you can see the two source registers. You can see the destination register, the opcodes, etc. So, again, this is no different than what we saw in tutorial 1. Here's the graphical format, which might be easier to follow. The bit fields are up on the left. So on the top left-hand side, you've got bit 31, and then on the right-hand side, you've got bit 0. So, again, in keeping with RISC-V, all instructions are 32-bit width. So this gives an example of the floating point at instruction single precision. So you can see the destination register and the two source registers. There is a floating point control and status register, and this holds the floating point flag field showing exception bits and the rounding modes that are available. And, again, we're going to cover these in more detail. So this table shows the format of the rounding modes as they are expressed in floating point instructions. We have static rounding modes. There are preferences such as round towards 0. So you can do this or you can round up. Again, we're very familiar with this type of operation. So the rounding mode itself is held within the floating point control status register. And you can see the bits that are available for this. So here's the bit fields. Round to nearest even values are actually preferred round towards 0, which we met in the previous screen. We can do round down towards infinity and so on. So, again, we'll write some programs to show how this all works. Also within the floating point control and status register, as we mentioned, there's a field known as the accrued exception bits field. And the meaning of these exception bits are invalid, overflow, underflow, divide by 0, and inexact. We can actually read these bits using the command floating point read CSR command. And this will read the register, and it places the result into a general purpose integer register. We can also set bits from a general purpose X register into the floating point control and status register. Later on, we'll be writing a program to generate some of these conditions, and we can read the floating point control and status register to look at these values. Here's our first RISC-V program, and it's very simple. It just adds two double precision floating point numbers. When we compile this, we're going to use GCC because we're going to take advantage of printf. Printf gives us a lot of capabilities in this area. So we defined a couple of constants there, pi and e, which most people here will be familiar with, and then we have a string. So we say .string and then pi, and then we see 15f, which is float 15 places. This was covered recently in an earlier tutorial to show the print specifiers that can be used with the printf commands. So the string is here, and then we use the f to signify floats. So the program itself loads these values into the regular X registers. And then after we've loaded the X register A0 with the value pi, we transfer it across into the floating point register A0. We do a similar thing with our number e, and then we add the two together. So if you look at that instruction f add.d, that means double precision. So we see it here, double precision. And then this is the destination register, and these are the two source registers. After we do this, we use this instruction where we put the value into A1. So, again, if you remember the print parameters ABI convention, we used A0, A1, and A2, and etc. like that. So here's how we move all the floating point registers into these different integer registers as well. So we simply call the result, and this is how we compile it. So, the output there is very simple. It says pi, and it gives you the value in double precision. Add it to e, giving you the value there as well, and it gives you this double precision result. So GDB is used here to show the contents of the floating point registers. Now when we use GDB with a text user interface, we can use the command text user interface register float or text user interface register all to show all the registers. Another useful GDB command we can use here is TUI layout next. So we get different windows to show us what we're doing, but if you want to look at all the registers, which I'm showing here, it depends on your screen real estate, but it's very useful if you can. So the program, as we said, simply adds two floating point numbers and outputs to the screen. Now if we look at a couple of the values in the registers here, we can see that the double value, double precision is 2.718 in this one. And then we can see in the other one, it's pi's value 3.14. But there's also a raw value here as well. So you can look at the raw value, and you can decode this as an exercise if you want. So this is similar to what we did in the first part of the program. Here's our second program. And, again, it's a bit large, so I had to fit it into two columns. The first part of the program is on the left. Next part is on the right. So this program shows how the rounding modes work. It incorporates many other instructions which are worth studying, such as conversion or the floating point arithmetic operations. The program should be entered and executed with GDB to really reach a full understanding of these instructions. The output gives examples of different rounding applied to large numbers. First we perform a multiply, and if you look at the output on the bottom right, we can see that dividing the product again does not quite give the same value as the original second multiplier. You can see our two least significant digits of 5 differs from 4 of the original number. The 4 rounding computations are put into the temporary X registers and loaded onto the stack. They are then popped off in turn to provide the second printf parameter. The integer result rounded to nearest is 52054. The integer result rounded up is 52055. Rounded down is 52054, and finally round to nearest magnitude gives 52054. This next program interacts with the floating point control and status register. It generates an irrational number. The square root of 2 causes a condition with the floating point control and status register. The control and status register is read with the instruction frcsrt0, placing the contents of the status register into register T0. The in instruction holds a value called flag mask, which is used to zero out non-status bits such as the rounding mode fields that we've already discussed. The comparison branch if equal instruction checks to see if any of the exception bits were set. And if so, it prints out the exception flag settings. In this somewhat simplistic example, we knew in advance that an exception would be caused by the rounding error when we squared root 2. In reality, each bit field will be interrogated and the printout will display a set of messages. So now this example shows the program running under GDB, and it clearly shows where errors can occur with floating point. The square root of 2 is an irrational number, and this means that generating the square root and squaring it back does not necessarily give the same result. This can have consequences, especially when using comparison instructions. In this example, when rounding could be used or even should be used. As discussed, the program reads the contents of the control and status register to see if any of the flags have been set. In this case, the value returned is a 1. There's a printout of the flag bits shown in the program, and we can see that the inexact bit was set, which is what we expect. The GDB command info register FCSR can be used to show the contents of the register. So here's more detail. Inexact bit. We saw that by putting in the command info register FCSR. And if you actually look at it, it is indeed inexact. So we start off with the value 2. We got the square root of that, and then we multiply it back in. And now you can see that there's a trailing 4 from it, so it's not exact. So after the conversion, FMB has been executed, which moves between the X integer registers and the F floating point registers. The contents of the integer registers represent the 64-bit double precision floating number. It can be decoded to generate this number as well. So here's the number here, and you can decode that too. Previously, we discussed not a number and infinity. There are actually two types of not a number. one which signals an exception and the other which carries on processing without generating an exception. There are also subnormal numbers which may be too small to be normalized in the format 1 point. Remainder of the number. So 0.0000, etc. These numbers are actually very close to 0. So these are subnormal numbers. So here we have a table listing these classification types and their definitions and the bit fields here. So negative infinity is when bit 0 is set. Negative normal is when bit 1 is set. Negative subnormal, you can see there, and so on all the way through right up to quiet, not a number. The next program will generate some of these classification types, namely subnormal and quiet, not a number. It will generate the subnormal number by first performing some integer arithmetic, and then it moves over its value to the floating point register. It uses division to reduce the value further. Earlier in the tutorial, we showed how to recognize some non-numerical patterns by bit fields in the exponent field, etc. The F-class instruction has two forms, fclass.s for single precision and fclass.d for double precision. Here, we will assemble the code using the regular AS and LD instructions rather than GCC. We have no need of printf here in this case. GDB shows the classification of the F2 and the F for registers after computation. Register F2 will hold a value smaller than could be represented by normal numbers. In other words, we can't have a 1 to the left of the binary point, and it's therefore classed as subnormal. Register F4 was used to calculate the square root of -1, which is a complex number and is categorized then as not a number. So we're getting near the end. What I've done here is to show a list with the majority of the floating point instructions. In this tutorial, we've used a 64-bit SBC, so results could differ on a 32-bit system. My recommendation is to use real single-board computer hardware, as not all simulators will support floating point. Also, I cannot stress enough that these tutorials should not be watched in isolation bereft of actual coding and execution. Okay, that wraps up tutorial 8. There is a lot of literature on floating point as well as great tutorials on this subject. The standard as mentioned is IEEE 754 and is adhered to by processor vendors. Finally, the links to this tutorial and accompanying documentation are freely available at risccomputing.com. Thanks for your time, and the next tutorial will cover some of the vector-supported features with RISC-V. See you in tutorial 9.